Hello, this is Richard Leeson, and today we're going to talk about the last steps of calibration for our facility loads, what we're going to look at, and what decisions we'd want to make, and then add an alternative and add the base case, and then look at what the base case is and where we want to go with our adding alternatives as we do that here shortly. So what we're going to do is we want to start with quickly. We're in our facility loads. We've run the inputs. We've made some changes in the inputs in the baseline to reflect what we think the building stock looks like, and we've come up with our initial results. And we'll talk a little bit about the type of changes and calibrations that we would want to make. But anything that shows up in this color here, it has been changed, so it's fairly easy to run through that and see what changes have been made. So you can quickly run through the list, and there's a lot of other changes that could be made and you do this as you know more and more about your existing facilities and buildings. Doing that, and when we get to the package selection, there really isn't, because it's going to automatically assume the baseline package to show up in the results. And then we've started with the site summary, and we're going to look at those results again. And what we see for our 53 facilities and about 3.2 million square feet, we can see what the site electric is. Remember, this is the annual consumption numbers. We do have all the individual facility groups displayed here, but what we want to look at, we're going to look at the gas intensity, which I see is about 68, and the electric intensity, which is sitting at about 52.5, and then of course our total intensity, which is 120.4 kBTUs per foot squared. So we want to see that, and what we've done is that it's all the facilities rolled up, and what we knew back here at the beginning when we put our consumption in, when we look at our consumption for our electric utility, is we knew the consumption for a larger meter area, which was about 5,408,000, or about 5.5 million square feet, and we have the consumption and the amount for that for our electricity, and we have that same for our natural gas. And with that natural gas, we see what the input unit is in therms here. We can't change it and have this convert. On the input side, we assume that this unit we know this unit in this amount, and changing those would just change how this number is recorded. It won't change this value. But that's not true when we get to the output side. So if we look at the results for this, we see we got the 5.5 million square feet. And if we look at the output results, we do see that we can change those. You can see that change there to 5.5 million square meters. So the output side does change. Okay, and we look at this area and this usage, and what we want to do is be able to get some idea of how our simulations is comparing to our overall meter. And in many cases, especially for installations, is that there's one meter, not individual buildings. It's moving in the direction of individual buildings, and if you have that information, that's great, because then you can take that and you can kind of calibrate each individual facility group to get something closer to this. But what we're looking at here is 1 meter for this for the facility. In this case, if you remember from our installation section, is we have some of this, it's on a loop, and so there is only 1 meter in that case for the energy that's being consumed. So what we have here are these usages and these site and source energies. Up here we have the electricity, gas, and then we have this common, and if we change this common unit to kBTUs, we see that these last two have changed, converted from this to this, and we can see that happens if we convert those to kBTUs. Now we see those are the same, and the same here. If we do the gas, we can see that. So what we're going to do is we have this information here in kBTUs, and we have this area here, and what we want to do is see how that compares to that 120 that we found from our simulation results. So what I've done is I've taken the kilowatts and therms just to see that those numbers did add up to what we had, and we wrote down the 326. We can see that that's sitting there. That 326,482 is sitting right up there. And if we convert that back to kilowatt hours and therms, we'll see the 95 million kilowatt hours and a 3.782 million therms, and we see that those numbers here are the same. But what we want to do is type in the 326,482,016. That's for the electricity, and that's in kBTUs, and the 385,809,376 for that. And then we want to put the total area in 5,408,901, and we want to find out what these intensities are. So we take we'll sum those up, and we're going to take those and divide by the areas. And we see that's about 60, and we had about a 52 on our electric. And that's about a 71, and we had about a 68 on the electric there. And if we add those two up, we have 131.2. And so the question that we look at when we look at these numbers and we compare it to the 52, actually we said 52.5 for that, and the 68, and the total of that was 120.4. We want to look at these numbers and say, you know, are we in the ballpark here? So here's things that we want to look at initially, and we want to talk about. And one of the things is that when we look at the difference in our electricity, we know that this is a site number, and this entire site number has other things than just the building contribution to it. And so we have pumping stations, we have sewer lifts, we have things that are outside of the building, street lighting, ball field, athletic field lighting, a lot of different things. There's water coolers that are sitting out in these places that are not building driven, and so our models will not account for all that unless we somehow put that information into the program. And so I expect there to be I expect the electricity to run higher than what we'll see at the installation meter, than what we'll see coming out of the summation of our buildings. And it's not that the building models also have other things. I mean, they're things that are not accounted for. We're looking at a meter that had last year's weather, and our building models are simulated with typical weather. And we don't want last year's weather to simulate. We want typical weather, so that when we predict, we don't predict an extreme high or an extreme low on the weather. We predict what's going to happen typically from year to year to year as we're looking at the planning aspect of these studies. When we look forward, I see differences in The weather is when it's put together by, it's called a typical meteorological year, or TMY. Um, it's made of average years out of 30 years of average data that comes out of this. So the weather file we're getting is automatically different. And then of course there's always model assumptions and model differences, a lot of subtleties. And what I look for is to try to operate within a, kind of a plus minus 10%, or try to, on a total, I try to be within kind of like 10 to 20% of the differences. And on the gas side, I see that's closer. And I notice on the gas side, there's like, once again, there's other things that are not accounted for by our building models that are in this. And we do heat uh, small buildings that would not necessarily be accounted for in studies. There's other usages of gas, including a small amount of leakage that can happen. So there's other reasons why the gas can be a little bit higher. Typically, it's not quite as large a difference between what the buildings are demanding and all the other sources. But once again, if you're looking at an installation meter, it's accounting for more than just what we're seeing with what the buildings are demanding in general. As we get to building meters, then we should start seeing these tighten up, and then we'd want to make more modifications to the model if they're typical operations of the buildings that we're looking at. Once again, not if if that building was shut down, or you had a unit that was deployed, things like that can change the meter reading. So you have to understand what's in your meter as well. So the models are really good at taking your inputs and looking at what's there, and then going on and projecting future changes, given only the changes that you've specified, not all the changes that can happen in a real world that we get that happens to buildings, be it weather, operation, and so forth. So the models are really good at doing this delta prediction. That's their strength. And so what we're trying to do at this planning thing is we want to focus kind of on this delta result anyway. So we want to get close. We want to get in the ballpark as we go forward, but we also want to make sure that we're kind of close in more of the typical behavior. But going back to our model, what we want to do at that point is, if we see something that has more of a discrepancy, and this definitely catches order of magnitude errors that you might have put the money in wrong, you might have put the gas units in wrong, definitely catches order of magnitude errors. And so we always want to take a look at that. But we also can go back to our models, look at those results, and then come back here and think about the building stock that you have. Did I capture in these in these pre-1980s or this mid-century models? Did I capture any? Is it extra leaky compared to compared to what I'm simulating? Is the envelope better or worse? Is the equipment better or worse than what I'm looking at? So those are the types of inputs that we want to look at as we're looking through this building list, and see how they compare to that average. And does it make sense if it's higher or lower? So the average here was 52, and the DFAC is sitting at 121. Does it make sense for that DFAC to be that high? And if you say, well, I want to take a little extra look at that, that's great. You go back and look at the gas and electric for that, and if it makes sense, then we're good, because like I said, we're going to concentrate on that delta change as we make it more efficient. That's the area we're going to concentrate on in our planning. Look at this from a planning level and going forward from that perspective. So the key here is to constantly to go through. We'll go back here and make our changes to these models and resimulate. And what we want to do is to make sure that we're happy with our baseline model before we go forward. So we want to spend a good amount of time, just like we did in the cleaning stage, to make sure that the data is good, and then come back here and make sure we got a good solid baseline before we move forward, because it'll decrease the amount of work that we have to do later if we actually put the work in now and get it and get it correct. So like I said, we can go through and we can look at all these different models to see if we've captured the envelope in the wall and exterior insulation. If we look at the air leakage rates, which has the envelope leakage plus the operation of the building, door closings, opening and closings, people going in and out of the building, captures both of those for the simulation. Look at the equipment. Remember that the equipment here is just to give us an idea. We'll actually get, depending on what we do in the installation section, we get a different look at the equipment, and possibly we want to keep this in line with that from an individual contribution to that load. But the building does demand this at the coils and not at the machine level, so it's not demanding fuel, it's demanding heating and cooling when we go onto the installation section. So like I said, spend the time here, do your due diligence up front here, make sure that we've got this in good order, and then from there we can move on to adding the alternatives. And I think we'll do that in our next section.